Yeah, let me begin by thanking the organizers, especially Amit and Partha, who've been around and sort of, bustling everyone up to participate very actively in this program. And there have been a lot of young students around, which has been fantastic. So this is sort of an informal seminar or, an overview of the kind of problems that people are interested in. Coming from not the atmospheric background or the nonlinear dynamic sort of background, but from people who are essentially working with turbulence, with turbulent transport problems, from a more statistical physics sort of background. So I will, so just interrupt me. I mean, there's no need for me to finish the talk as such, so interrupt me as and when things start becoming a bit unclear. And I will sort of try to minimize the algebra a little here, so whoever wants to sort of know the details, you can always catch me since I'm in-house. So, all right. So let's get started. So I think it's always a good idea to have a picture in mind of what exactly I'm talking about. So the results that I'm going to talk about are equally applicable, I mean, equally within quotes, to cloud formation, microphysics of clouds, to pyroclastic flows, to planetary formation, and a wide variety of things, and more recently, a lot of interest in these marine biology, patchiness on ocean sort of problems. So I'll try to provide a very general framework, and then we'll try to understand how certain numbers help in understanding clouds, because that's sort of one of the areas that the school has been trying to look at. So in general, when people like us talk about particles, we, for lack of imagination, we always have sort of three kinds of particles in mind. One is what's known as traces. So, you all attended Jayanta Bhattacharya's introductory courses on turbulence. So he talked a lot about traces, which are essentially mimicking the fluid particles. So think about a drop of ink in water. Or we are talking about heavy particles, which in a flow, which would be something like water droplet in air. Or we are talking about light particles, which would be air bubbles in water. All right, so light, heavy, or neutral means whether they're more dense than the flow below or they're less dense. In general, whenever you have particles which are not exactly tracers, but which are different from tracers, so for example, water droplets in air, which is often the setting in a warm cloud, what you end up having, and these are sort of results from experiments and simulations, what you end up having is an inhomogeneous distribution of particles in your system. So you do not, so ink, the whole water turns uniformly pale blue. That's a homogeneous distribution because the blob of ink has sort of mixed well in phase space. But if you have finite sized particles with density different from the flow, they don't mix at all. And so essentially you have clumpiness. There are areas where you have more of them, and there are areas where you have less of them. Now it's an equation I won't sort of even try to explain. The only reason I'm going to yeah. Simulations, experiments. What is changing? The size of the particle, you could imagine, or the density of the particle. Either way, I'll come to it. The effect is the same. Okay? I mean, if the radius square changes in the same way as density, you get exactly the same picture. All right. Okay. So, of course, since I'm a theorist and we would like to do a theory for this sort of problem, the first thing is, can we write down an equation of motion for a single spherical particle in a flow? All right, so this is sort of work from about a few decades ago by Maxey and Riley, where they looked at all the forces which are acting on a little sphere of radius A under certain suitable assumptions, but don't worry about them for the moment. And you come up with a rather sort of complicated looking equation for someone doing simple asymptotics or numerical simulations to digest. So this is the famous Maxey-Riley equation, which looks at all the forces which act on a little drop of water in air. All right? However, one can sort of make enough simplifications to this equation, and then what one ends up essentially having is an equation of motion. So this is sort of valid for a water droplet, a nuclei water droplet in a warm cloud, what sort of one ends up getting a system of equations which is rather simple. If x is the position of the particle, dx dt is equal to the velocity, and dv dt is equal to 1 over tau p, some characteristic time scale of the particle, and I'll come to your question, Amit, in a second, multiplied by the slip velocity. So u is the velocity of the fluid, and v is the velocity of the particle, all right? So this sort of looks nicer than the equation that I showed you before, and you just have to trust me, it's a short talk, that when you do certain reasonable approximations which have to do with that the size of the droplet is small and the suspension is reasonably dilute, etc., you end up with this equation. All right, so for the rest of the talk, I'm going to work with this rather simple equation and try to convince you that that indeed throws up interesting ideas, and which are not completely sort of a theorist's pipe dream, but they actually work in practice. So with that sort of introduction to the setting, so the setting, it's clear, I'm trying to model water droplets in air. That's what you have up there. The water droplets, the dynamics of the water droplets, I'm modeling trivially by this equation, which comes from the Maxey-Riley equation known as the Stokes drag model. I haven't discussed about u, which is the advecting flow velocity, but you will soon see that I obtain it from the Navier-Stokes equation and sort of close the system of equations. All right, so what's the now for the introduction, really. So what are we interested in? So the overall question that one tries to attack is the fact that in warm clouds, which are common in countries such as ours, we would expect that the turbulent airflow enhances collision coalescence rates in droplets. So if you go back to the older work of Zaborowski and other sort of very good atmospheric sciences, they would have measured various quantities and would have tried to argue, both observationally and otherwise, that turbulence doesn't play a role. In the next 20 minutes or so, I will try to argue that turbulence does play a role in a way which makes us happy. All right? So, and then we'll try to see that this idea of preferential concentration, which Amit was asking a few minutes ago, and the fact that there is a turbulent airflow, does this help us to understand why you get rain typically in 20 minutes or half an hour or something, all right? Don't remember that time towards the end of my talk and ask me to compare the time scales I obtained, but that's what we are after. And we'll try to develop an understanding through experiments, theory, and direct numerical simulations. So to make the questions more precise, what we want to understand is how fast do droplets collide? How frequently do they collide? If they collide, do they coalesce and grow? Then how fast do they grow? Because, of course, we do have some ideas about nuclei starting with 10, 20 microns and raindrops being 1 millimeter. So we would like to know how do they grow from that micron scale to the millimeter scale. And some of the stuff that I'll be talking about are included in these references over the last year and a half or so. All right, good. So our approach, we take the fluid velocity as the Navier-Stokes equation, exactly like what Jayanta Bhattacharya was teaching you all a month and a half ago. We make no approximation to the Navier-Stokes equation. We solve them using pseudospectral methods for accuracy. And we work typically in homogeneous isotropic turbulence. And the particles, as I told you, are droplets. Obey that rather. Just to remind you once again, that's the Navier-Stokes equation, which you all of you have seen. And then we solve for this, and at every time step, we feed the u back into the trajectory of the particle. We need to interpolate, of course, to the particle positions and solve for the particle trajectory. So that's the setup. Is the setup very clear? Because after that, I'll just sort of tell you what comes out of this setup without doing a lot of math. So if the setup is clear, we can sort of proceed. So just to sort of give you an example, especially the younger people, about the sort of systems that are going on currently in the world. So for three-dimensional Navier-Stokes simulations, our computers present day can reach up to about 500 microscale Reynolds, which is certainly much better than any terrestrial experiment, but much smaller than anything extraterrestrial in nature. And we are now able to track about 10 to the power 9 particles in our simulation. So the reason why we choose such numbers, and we can discuss this later, of course, because the physics is not depending on this. So these numbers are essentially chosen to mimic the mass loading in an initial sort of warm cloud as it builds up. So it's sort of, these numbers are taken from various reported numbers to try to get the initial mass loading correct. Yeah.
The resolution in each direction, how many points are
2048, 2048, 2048.
And you have something like 10 to 3 particles.
That's right, but the particles are off-grid also.
Yeah. Off-grid.
Yeah.
But you need to do interpolation.
Oh, yes. Cubic, trilinear, if that's your next question, and spline, all three seem to converge. And the large simulations typically...
Basically, you don't have the small-scale information of the velocity.
No, our velocity fields are resolved up to half eta, half Kolmogorov scale. So we do have enough in the small scales. But sure, there's an interpolation error, but that is, we've checked with different resolution, that converges. So, I mean, I don't think that gives the source of error. I'll comment on the errors in a bit. And so the large simulations ran for about 8 months in a sort of 60,000 core parallel machine. Smaller ones were a bit smaller. So they've been running for and wasting a lot of electricity and adding to global warming. All right, okay. Yeah, oh, sorry, it's being recorded, right? Yeah, okay, fine. So the point is the following. So what we are really worried about, the reason why we feel that turbulence will play a role has to do with what's known as turbulent mixing. Again, something which was probably taught in the classes here. And let's look at this following snapshot so you get a visual idea of what turbulent mixing is all about. So this is color-coded in such a way that the dark-colored patches are fluid elements which are in a given time tau, how far they've traveled. So basically, you will see that the dark and the light-colored patches form various fronts at various, and people try to characterize the shape of this front, etc. But that's not my purpose. All I'm trying to say is that turbulent mixing allows a lot of inhomogeneity in the way your fluid circulates. It's actually right here. All right. So let's come back to the questions about how valid these equations are, etc. So the first question that we wanted to ask was, yeah. Yes, so there is a notion of clumping, but here clumping is not the effect because it's a scalar field. So these are like tracers. So what
I'm saying that why is it that particles which have traveled this are kind of clustered together?
Oh, you mean the voids? But this is an artifact of because I've really zoomed into a small patch. So if you zoom out, you will see these patches change. So there is no a priori reason that these will be smaller patched places. Okay, good. I should change the picture to avoid this message. All right. So as we discussed, the equations that we used looked a little too simple. So I could argue mathematically that they're sort of valid, but it's better to sort of argue through pictures. So in this plot, what we are looking at is the probability distribution function of the relative velocity of two droplets which are about to collide. So you take the velocity difference between two approaching droplets when they're really close to each other and measure the PDF of that angle for different sized particles. All right, so these two plots correspond to two different sizes of the droplets. Sorry? The order of eta, the smallest scale in the problem. All right, so let's look at any one of these. Let's look at this plot. So the symbols on this plot correspond to data which we obtained from experiments which were done in Göttingen for the same size particles. Apparently, the experiments are much harder than the simulations. And the lines, the continuous lines, are the data that we obtain from simulation. So we also have a theory about the functional form of this PDF, but that's not, so that will distract us from the main message. So the main message that you see is modular certain discrepancies on the right tail. So these are details I won't get into because it's really more turbulence and this stuff. But modular that, if you look at the left tail, you find remarkable agreement between experimental data and numerical simulations. And of course, the theory is also plotted there. So that's and this is sort of another way to show the same thing where we show that we can collapse the different PDFs. So the point is that even such a simple model as the Stokes drag model can actually give us meaningful results about the nature of collisions amongst droplets. And these are all done in settings which are mimicking, just to re-emphasize the point, what's going on in warm clouds. Yeah. Am I worried that they don't work? That the equation doesn't work?
That's what your worry was, and then you shot.
No, my worry was trying to convince people that a simple equation of the form dvdt equal to minus gamma v minus u actually works so well.
Then what is the importance of particles?
So there's a physics reason why we made that measurement. That was because, as I'll come to the next slide, we wanted to see what the velocity of impact is. Do they hit so hard that they fragment? Or do they hit, are there extreme events? I mean, okay, so the physics question is the following. How broad are the tails? When particles collide with each other, so you are measuring stuff when the separation is very small, they're about to collide, you would like to know whether there are extreme events in these statistics, whether you have a large tail in the distribution, all right? But for the moment, I'm presenting this plot to sort of convince people that the simple model I presented without much justification actually works. So what's the?
What's a V parallel positive and negative? Positive means what and negative?
Oh, V parallel is the relative velocity projected on this line. So negative means they're approaching, positive means they're going away. So when you project it, so just take V2 minus V1 vectorially. So the way you choose it, if it's negative, it means that they're approaching. If it's positive, they're going away. The curious thing is disagreement when they're going away between experiment and simulation. Sorry?
It's not symmetric.
It's not symmetric. And that we know that has to do, there's a lot of nice work. I mean, JKB talked about all this anomalous dissipation, etc. There is recent work via that to understand why it's not symmetric. For a fluid, you can show it trivially that it won't be symmetric because you will lose energy. I mean, it's as simple as that. That's why the right tail is much more subdued. Okay. Right. So, yeah. So this is essentially where we were able to sort of contrast numerics and experiments very well to justify the sort of model that many of us have been using for years. But I talked to you about the PDFs. But after all, if we are doing measurements, I mean, why should I worry about the PDF? I would like to understand what's the most probable values of impact, right? And typically, I would also like to understand whether the value of, whether you have two identical particles, identical water droplets when they hit, and when the two droplets have different sizes, how does impact change? For example, a question in this business is there a snowball effect, which is a large drop zips through a supersaturated vapor field where there are small droplets around, picks them all up, and settles, all right? So here what we looked at, so this is with my master's student, Martin, was computing exactly at the point of impact, what is the velocity difference between the two particles characterized by their Stokes numbers ST1 and ST2, and trying to understand, so data from numerics, both in 2D and 3D, the curved lines where possible are our theoretical estimates. So what's the take-home message? The take-home message is the following. Suppose you have a particle of Stokes number 1 of radius, a given radius, in a sea of particles of all sorts of radius. So think about the nuclei which has grown through condensation to about 20 microns. Others have grown in the meantime. So this 20 micron is moving through a sea of particles which have all sorts of radius, droplets. What about the impact velocity between this droplet and the others it encounters on its path? Does it become increasingly large, or is there a saturation? All right, because now people are trying to model fragmentation through these, so that's why these are important measures. So what we found was that the velocity of impact as a function of the Stokes number, keeping one fixed and varying the other, seems to saturate as an exponential of -1 over Stokes. That was the theoretical prediction that we made, and the sort of numerical data seems rather consistent with it. So what it tells you, if I go back to the PDF picture, although I had reasonably fat tails, but I'm still bounded. They will not grow indefinitely. All right? So all of this sort of leads us to the question which one tries to answer, and it's the following. In most clouds, you will have an initial condensation phase through which you create nuclei, which are roughly of the same size. There are variations, but sort of roughly of the same size as far as the theorist is concerned. Now you want to know, you put them in a turbulent flow, because it's turbulent up there, and you allow them as they move around through the dynamics that I've described and tried to convince you that it's sort of all right. We've looked at the impact velocity, we've looked at the PDF of their relative velocities, etc. But now let's ask the question, what if they were to coalesce? How fast do my largest droplets grow, and do they grow fast enough to agree with observational data? Now, if one were to do a sort of mean field theory of this problem, one would begin with the Smoluchowski equation. Start with a monodispersed system, have an asymptotically flat coalescence rate in lambda. One can solve that equation. If you have an infinite bath of the first set of particles, one can sort of do it even analytically to an extent, and one finds a rate at which the number of particles grow. So the setting is you begin with capital N particles, all of the same size 1. As time evolves, capital N2 particles start appearing, which are adding masses of 1 and 1. Then 1 and 2 gives you 3, 2 and 2 gives you 4, 1 and 3, etc. And you build up. And you want to know how fast do the largest droplets grow in this problem. Okay. So it turns out that even for this problem, and I'll sort of end with a small exercise where I'll sort of show how one can do theory for such equations, even with Navier-Stokes. It turns out that one can actually, under reasonable theory, and so that's done in this paper a few months ago, one can actually come up with an analytical estimate of the rate, the lambda, the rate in the Smoluchowski equation, the rate at which particles grow, and also if Ni is the ith size particle, so you begin with 1, so how fast do the particles of mass 2 grow, mass 3 grow, one can come up with a sort of, under suitable assumptions, one comes up with a closed form expression of the how fast does a 20 micron particle grow. So if you were to ask me, I start with all particles of size 10 micron. I want to know in 1 hour how many 50 micron particles I will get. All right, so that's what this expression means. And I'll tell you, plug in 50 here. Don't do it, but you could do it. Plug in 50 here, and you will get the answer. All right? So, and it turns out that these are all universal constants. So these are the famous universal constants that JKB was talking about for the third order function in his class. So when you do that, you can start comparing both for the lambda and the 2 analytical predictions that we had with data from numerical simulations. So this is the monodispersed particle, which was a million, 10 to the power 9, whatever that is. And then you had particles of size 2, which are growing in time, size 3 growing in time, size 4 growing in time. And the dashed lines are the short time asymptotic analytical predictions that we obtain. Okay, so there are 2 things. One, of course, it's good news that at least our short time asymptotics seem to work well. The agreement isn't bad, especially when you look at the PDF slopes. The agreement is pretty good. 0.27 is the theoretical prediction. However, it's sort of saying something a bit more. What it's saying is, we started with this idea that most mean field theories get the time scale at which rain is triggered wrong. You overestimate it. So if rain happens in 20 minutes, your theory sort of often tells you it will happen in 2 hours. All right? So with this approach, what we found is when you look carefully and think about these exponents, you will find that above mean field, so mean field would have been when this delta 3 was 0. There was no correction. This correction effectively allows you an accelerated growth rate in the problem. And so that's where the focus now is, look, I mean, here's an example where we actually show that turbulence seems to enhance the growth rate of droplets in a warm cloud. I'm not claiming that it's anywhere close to what will be observed, but this is one way in which one can understand why there is an accelerated growth in the droplet sizes. Okay, so I will skip this issue about transients because I have 4 minutes and I just wanted to give a flavor, especially for the students, just to tell you how one can do calculations with these equations, even though there are Navier-Stokes and stuff floating around. And the way I will do it is to address this last question, which often if you open a lot of journals on atmospheric physics, there was a fantastic paper many years ago where people measured the settling of water droplets under gravity in a cloud. You have gravity, you have turbulent fluctuations. In high school, we learn about this terminal velocity, etc. But when you have turbulent fluctuation, as a function of size, does the settling velocity change or not? And there are lots of very nice papers in the 80s and 90s which dealt with this and what it implies for rain and clouds disappearing and non-rain, etc. So we tried to investigate this problem again in simulations. And the question we were asking was the following. Remember, gravity is pointing downwards, so it's in the z hat direction. So the question that people have been bothered about for a long time is what is the average settling velocity of droplets in a cloud? So what one does is one takes the velocity of each droplet, project it in the direction of gravity, and take an average. I mean, as simple as that, right? Now, if I go back to that sort of rather simple equation of the Stokes model, one can actually try to compute what the settling velocity is. The first bit, there is no cheating at all. So if tau p is the time scale of the particle, then if there was nothing else, the particles would fall with tau pg, right? So you have a particle of size this, there's gravity g, so you fall with the terminal velocity tau pg. All right? If there is turbulence, etc., you're typically not likely to fall with tau pg, but you're likely to fall with something called some other velocity vg. All right? And the idea is to figure out if one can estimate what this difference in velocity is. Okay? So let me give you the results first because I realize it's just 2 minutes left. So this is a plot that many of you may have seen, or at least it's very common in the atmospheric community, is the average settling velocity as a function of the Stokes number, where you have this bulge and then things come down. And the idea is it possible to explain every bit of this graph? So it turns out it is, but maybe after, in the evening, whoever's interested, I can do it on the blackboard. And it turns out that you can actually predict what the settling velocity is. And here's a sort of proof of principle. So that's numerical data. And you can theoretically show how the settling velocity depends in particular on the Reynolds number and the Stokes number. And the agreement is rather remarkable. So that's observational, numerical, theoretical data all clubbed in together. And the scaling is rather interesting. That's because this tells you that the settling velocity increases as a positive power of the Reynolds number. So in places where you have airflows which are much stronger and the effective Reynolds number is much higher, you will, so what I did not tell you is under gravity they follow special paths, but you will have a sudden acceleration of, actually a wrong word, you will have a sudden onset of settling of droplets which decouple from the flow and start falling down. And that's sort of captured in some ways when you think about it in this sort of function, which are where you have a scaling form in terms of all these non-dimensional numbers. Okay, so I just finished here. So what are the open questions? So we've sort of tried to grab the problem in many different ways. Because it's a mixed audience, I just wanted to give a flavor of what's possible using simulations and theory to actually look at the microscopics of this effect, which has to do with droplets, moist air, etc. We've sort of tried to attack it from many different ways. We've tried to understand how fast they hit, whether they fragment, whether they settle, etc. But what we still do not have, and that's the challenge, the incomplete theory still is to have the full collision kernel, which incorporates Reynolds numbers, particle sizes, and gravity, and the sort of dominance of gravity over turbulent fluctuations, apart from, of course, harder questions such as realistic geometry, etc., which we don't have, of course. So I'll stop there. But I just sort of, this is just to tell you what can be done, and then we can always meet in the evening for all the rest of the details. Thank you.
Any questions?
I have a nice question. Probably don't effect on the shape changes.
No, that's why I said realistic geometry is for the shape. So we don't, but there is a way now that can be done, which is through what's known as the Kahn-Hilliard model of Halperin and these guys, the model B. So there you can automatically have the shape changing. So that's what some of...
Pattern formation.
Exactly. So we are, yeah. And Rahul, for example, works on that a lot. Yeah.
Any other questions?
Yeah.
There is going to be intervening airfill between the two approaching droplets.
Yes.
So unless you model a two-way, so the pressure can build up in the airfill.
Oh, sorry, I should have thanked people who enrolled. Yeah.
Unless you model the coupling between the droplet and the flow.
Yes.
There could be this airfill pressure build, the lubrication in the droplet. So in which case the droplets do not come close together at all. So in that case, your PDF will kind of...
I agree with you, except that's what I've always been told. But when you actually do experiments, so you're right, I mean, the lubrication and short-range interactions, they can be modeled, they're a bit cumbersome, you can always take a short-range force. They can be modeled for sure. However, when we actually started comparing experiments and numerics, it does seem that that's such a sort of subleading effect that it's all right not to worry about it at all. I mean, that's what the data seems to suggest, but there are stronger reasons for that. So, I mean, there have been other papers which showed that the hydrodynamic interaction leads to a renormalization of the Stokes number at short scales. So I know that's what fluid dynamics people tell you, that you have all these lubrication which must matter. I'm sure it matters, but in a very turbulent medium, okay, this is, in a minute, this is what I will show to say that it probably doesn't matter when you're approaching. That's all. But it does, you're right. I mean, it's a short-range force, repulsive.
All right, let's thank Samriddhi again.
Thank you.